Welcome to my YouTube channel, and today we'll be looking at the high fidelity. It says there, actually. I don't know whether it is high fidelity, but it's a Pye Mozart. I think it's yes, it's called a Pye Mozart HF10. That's right. Had to look it up. A Pye Mozart HF10 amplifier. Four of them came into the workshop. This one was the worst for wear. It was in quite a state. I think it had been left in a garage, judging by the amount of dust on it. Anyway, it's supposed to be a 10 watt RMS output audio amplifier, made between the years of 1957 to perhaps 1962 or thereabouts. It's quite small. It's probably only 12 inches by eight about 8 inches by about 6 inches deep. So it's quite small. And on top you can see that there's plenty of air ventilation here available, because quite simply there's a sideways mounted EL34 in there. I don't know whether you can pick that valve out, but that's an EL34. And the circuit design is that it's a Class A EL34 pentode output amplifier, supposed to be delivering about 10 watts. But if you're lucky enough to own one of these, I'll just show it to you. It's called the Mullard Technical Handbook. This one's volume 1, which was printed in 1960 for receiving valves and equipment types and so on. And you look up the EL34, you'll see that in Class A, and this one has a fixed bias of 13.7 volts on the EL34 output valve, that the distortion is about 10%, with about 10 or 11 watts of output. So that's quite high distortion for high fidelity, if you can see that there, if you can read it. So I looked at this and I thought, well, is this cranked up to be all that it was supposed to be at the audio fair in 1957, when it caused quite a stir, apparently? So I thought I'd just look into the circuit and see just exactly what it was. And it's quite a straightforward circuit. So without any more of ado, we'll have a look and see at this circuit. So we see here we got these inputs, tape record, tape, radio, and I think that says pickup. And the pickup has various adjustments to adjust the various input impedances of the different cartridges that may be connected to it via the circuitry here. So it's quite interesting that was a selling point of the amplifier in 1957. Anyway, if we look at the circuit, we've obviously got some kind of gain here in the first stage, which is an ECC83 double triode. So the losses incurred here in this input circuitry are made up in this first stage, and the losses in this tone control network, bass and treble here, are made up in this second stage of this ECC83. So that is the valve lineup, the ECC83 double triode, the driver, pre-driver and driver of the EL34, EL34 is here, adother ECC83 double triode. So, so obviously the advertising literature said that for 10 millivolts in on the, I suppose, the magnetic pickup here, you will get a full rated output here. So you've got to have quite a bit of gain going through these stages here. If we just look at it quickly, I noticed from the circuit analysis that Pye, if people that manufactured it state that there is this. I'll just show it to you. XL1 there, which is the bias diode, which is a germanium diode there, GEX34, and there's a winding on the mains transformer of 10.4 volts AC, and by the time it's rectified via this GEX34, we should have a fixed bias of 13.7 volts DC at its output, which is fed directly, more or less directly, to the grid of the EL34 output valve. And we can see that there via grid leak resistor, is it? What have we got there? 470k. That's a bit low, but it's not too bad. And it's then fed round and up to this XL1 germanium diode and a winding on the mains transformer to produce 13.7 volts. So that's how the bias is, fixed bias is supplied to this output valve. Right, so that's more or less it. The other interesting point is here is that feedback for the pre-stages here is supplied by a winding here, okay, which is also obviously, as you can see, the winding for the output loudspeaker windings. And there's a little, perhaps you can see that there says F, that's a little feedback winding feeding back down here and around to this second preamplifier stage here. So there's some feedback, negative feedback, and here across this part of the winding and down, is that to earth or common? Yes, we have what they call what could it be? Damping, they call it. So it's damping the output with this low value 1K pot. I'm not sure, and that is also fed into the cathode there. So well, what are you doing? I wouldn't necessarily put anything there, but still, that's what they decided. They needed some damping in the circuit, and if you've got a 15 ohm speaker, then you're going to have about 1 ohm. You're going to have about 15 damping factor. So I've been testing this amplifier at 8 ohms on the 8 ohm winding, which you can see down there. Anyway, enough of the circuit. I think it's just straightforward. Oh yes, I forgot to mention the fact that it, for its age, 1957 to 1962, it's using a bridge rectifier here. Normally they would have put a valve full wave rectifier in there, but they decided to use a metal rectifier to produce 270 volts from the secondary winding of the mains transformer, and some filtering here. This is, I think, 100 microfarads. So there's quite a bit of smoothing there, and it produces 270 volts, or should do, to feed the final stage. And then there's more decoupling here, smoothing, 16 microfarad, a double capacitor, single canned electrolytic, 16 microfarads each section. And at the output there you get 185 volts or thereabouts, and then here through that drop-in resistor you get 160 volts to supply the first stage. And interesting to note that there's 390k in each anode, so you should get about the same voltage on each anode, which you do. I measured it at 80 volts or thereabouts. So there you have it. Now, this particular amplifier came in a terrible state, as I said earlier, dust all over it. So let's just show everybody how you take it apart. Very simple. 2 screws there, and similarly 2 screws there takes the face here, the panel off the front, and then round the back we have two more screws. There's one there and there's one there. So I'll just pause this while I take the screws out, and I'll start the video again. Okay, I'm back again. Just show you that I've taken the side screws off, and this front here comes away. But it will do if I take the last screw out. There's always something you miss, isn't there? There's a screw there I haven't taken out. That's it. Yeah, sorry about the video waving around. And we've removed the two, I think they're 3BA or 4BA screws at the back. So they've been removed out of there and there. And then the whole thing slides out from the front. So I'll just show you that. Holding the camera with one hand, pulling that out there, revealing quite clearly what this is all about. So we have here the mains transformer, which is rather small. The whole thing is quite small, as I said earlier. Here we have the output transformer. So no, that's the, beg your pardon. Yeah, that's the output transformer, and that's the mains transformer. Have a look, yeah. So, as I said earlier, there's a sort of sideways on mounted EL34, which is the output valve. This had to have a new smoothing capacitor. That's a C2 in the diagram there. It's always best to change these smoothing capacitors out, just as a matter of course. This filtering smoothing capacitor there, and these here. These two on this particular one weren't too bad. So I used a variac, as I've done in my other videos, to just turn up the volts slowly to the required voltage in steps. So that's always very important. Otherwise you sometimes get overheating of the, in this case, C2, which is this one here. And this one's been replaced with I couldn't find 100 microfarads 400 volts, so I put a 200 microfarad 400 volt capacitor in there. So there's quite a bit of smoothing in here right at the beginning there, at the feed to the rest of the circuit. There's at the present moment this would have been 100 microfarads here, but this one's got 220 in it. Now, what I noticed about every single, I've had 4 of these into the workshop to repair, every single one of them had low voltage here. Now, this is important. Why was there low voltage there? Was there a loading in the circuit, or what was it causing this low voltage here? It was perhaps 220 volts or even less, which is quite a loading on there. So in the end, it turned out to be this metal rectifier. So I replaced, on every one of these that I had into the workshop, I replaced that metal rectifier with a modern equivalent, which brought the volts up here to, in one case, to about 290 volts. And I had to carefully select that resistor there to be a little bit higher, to drop the voltage to get to about 185 here. But that was the exception rather than the rule. Most times I did get about 270 odd or 280 here, which is about right. So if everything's if everything's working okay, excuse my voice, I've got a cold. If everything's working all right, here with this filtering here, 16 microfarads, you should get, and this dropping resistor here, 56k, you should get about 160 volts feeding into this first stage here, V1A and V1B. I was getting, at this anode here, something like 40 or 30 or 40 volts, very low, and it turned out to be a leaky DC blocking capacitors here. And what was happening was the DC was leaking through here, okay, round here and into the top of the volume control, and causing quite a bit of noise and everything here into the pre-amplifier stage, into the grid here of this second valve. So as is the usual case with these very old valve amplifiers, you should change these capacitors out as well, as a matter of course. Okay, and indeed, when they were changed out with non-leaky capacitors, the volts immediately rose to what you see here, 80 volts on each anode. So that was the first thing. So if we turn it over now and have a look at the underside, excuse me, just grab hold of it, turn it over. Ooh. And here we have the underside of a printed circuit board, and this was a selling point in 1957 for the construction of this. They sold it as a printed circuit rather than point-to-point wiring. Now, the first thing I noticed in the winding of this is the output transformer windings here. We have, I think, we have the DC's, the primary for the primary for the anode of the output valve. That winding, that secondary winding there, is there, and then we have on the output side we have the windings for the different speakers, which is down here. These windings in here. So there's the primary side, and then we have the secondary side here. Doesn't look as if it's a secondary side, but it is. Anyway, I noticed that there was a wire running from there to there, which is not in the circuit. And I'll show you where it is. It's a wire running from this F point, where it says where it says F, okay. Instead of having feedback around the circuit there, this cathode was wired straight to earth, okay, because this winding, or this section of the winding here, was open circuit. So being open circuit, there was absolutely no current being drawn through the cathodes to ground. These were floating above earth, above earth potential there, and so there was no output. So connecting this particular output transformer there, at that point there, down to ground, which is that winding, and this happens to be ground here, everything started to work. So this particular output transformer was 40, and the only way to get it going was to connect that across there, and someone else had already been in here and done that. So there's nothing I could do other than put a brand new output transformer in there, and of course very hard to come by, or you'd have to have one made, quite expensive. So at the present moment there's no negative feedback in here. This valve is straight down to ground here, okay. And so not this section, but this was straight down to ground. So there we are. Obviously, because this bottom part here is not, it should eventually, through this resistor here, end up down to ground. So that's the current path through all these cathodes here. Okay, they have to have a current path down to ground somewhere, and so obviously with this here and this here, there's no feedback on this one. So that was a real. The consequences were minimal, believe it or not. I'd expect to see more gain, but there didn't seem to be much more gain. Anyway, the next thing to do was to change that capacitor out, which you can see has been changed out, and it's this coupling capacitor here, C3. Okay, that was leaky as well. So all the coupling capacitors. That's this one. Sorry, yes, this one, um, this one, and this one. All 400 volts. Okay, working. Were all changed, and incidentally, the cathode bypass capacitors here, bypassing the AC to ground here and here on the first stage, V1A and V1B, was changed as well. That is in the circuit. That's that one, C23, and is that C12, is it? Or C10? My eyes are not very good. It doesn't matter. It's the cathode bypass capacitors. They were leaky or weren't very good, so they were replaced. So as you can see, more or less, most of the capacitors in this amplifier, and there are not very many, were replaced. I didn't need to replace this one, and I didn't have to replace that high voltage one there, which is, I think, C5. I didn't have to replace C5. I think that's C5 there. I got the circuit diagram from off the internet, and it was very useful because I could see where. There it is. There. Yes. It's Anyway. Is it C? It's that one there. I think doesn't matter. There's C. There's C5. I think it's C3. Oh, there's C3. Yeah. C3 and C5. C3 and C5. C3 and C5. So I had to change that. Well, I didn't change this one. Let's just focus in. I had to change that one. I just looked at this smoothing for the fixed bias and the germanium diode in there, and I measured the voltage at this point here in the circuit, where that germanium diode is there, and where it's connected to the smoothing capacitor here, down to ground. I measured the volts that were being fed out and round to the grid of the final stage, the EL34, and it was 13.7 volts. And if you look at the specification, the circuit analysis, as I said earlier, 13.7 volts DC output. I did have a look at this, they called it MR1, contact cooled power rectifier, which was, they were making selenium rectifiers in the 50s, and this was early development, which carried on into the 60s. Solid state rectifier, if you want to call it that. And this one would produce about 116 milliamps. It could deliver at 270 volts. So I observed that the EL34 was running at a plate, or as we say in Britain, anode load, anode E or HT load of voltage of 270 volts. So on my circuit I had written 270, and I expected to get 270 because that is indeed what is fed through a bit of volt drop through this winding onto the anode of the output valve. So the circuit analysis states that there should be 270 volts feeding, as it says here. E on HT end of anode load is 270, and 185 there and 160 there. So I've written all that in on the circuit diagram, 185 there and 160 volts there. And you get, what you get is 80 volts on, or should get 80 volts on these anodes, and 185 volt feed. You should get about 100 volts or thereabouts on these anodes here. If you don't, they're probably, if they're low, it's probably leaking capacitors. Okay, so if you do repair one of these, first port of call is change that out for a modern bridge rectifier, a very highly efficient one, rather than these horrible things that just no good really. They may have been all right in their day, but you know, you just don't get the voltage there that you should. So that's what you've got to look out for. I don't think there was much else that went wrong with them. Change the capacitors, the coupling capacitors, change the bypass, the cathode bypass capacitors, um, check the voltages, make sure that they are what they should be, make sure the fixed bias is neg 13.7 volts here, just there, at that point there, or at the grid, first grid, the V3, and that's it. I found that most of everything else was okay. The input circuitry, well, you know, who's going to use this as a, it's going to use this as a magnetic pickup, maybe. It would do to make sure you match your pickup using these two variable resistors, which are on the back here. They're these two here on this. Now, just turn this over and show you more clearly. And it says there compensator. Well, yes, it's compensating for the pickup input impedance of the input impedance of this to match the output impedance of the pickup, because for maximum transference of power or whatever, the generator, that is the pickup, must match the load, which is the input here. So that's the circuit theory. Maximum transference of power, you should match the generator with the load. So that's what that compensator is. So you just turn this up to get the maximum sound, I suppose, maximum output. It also probably, and it will, change the frequency response as well a little bit. Well, it did if you didn't have a pickup, a magnetic pickup. There's an RIAA curve here, in here, to match uh, magnetic pickups and crystal ones. So, but I think that this was really designed for magnetic cartridges. Really should be. Well, they state 10 millivolts, which is a magnetic cartridge sensitivity. And you've got tape input here, radio input. I tested this using the tape or the radio input, and for full output I had to put about 220 millivolts in here, which I suppose is a bit high. I should expect about 100 millivolts in here to get full rated output. And then there's this horrible damping control. I have to say, you know, what the heck? And there's a hum balance here. Now that was useful. Really, if the designers, let's just turn this over, if the designer pays attention to the way in which the heaters are wired and the way in which the heater wires are twisted, okay, as you can see here, I would expect this to be the type of twisting, the amount of twisting you really need to feed from the 6.3 volt winding of the mains transformer. And I don't like to see this sort of thing, but I suppose it can't be helped, where you have the twisting stops and then there's this sort of wire that comes around. Really, I know it can't. Here, let's have a look here. Yes, you've got this common here on the winding, and then you've got the actual thing there. So, and this is rather loosely twisted together. So there's sort of scope for a bit of hum pickup. So here like two parallel wires. Can you see that? Not twisted together very well there. And so this is it Humdinger? Humdinger, yeah, Humdinger circuit. That's what it is. It's just a simple RV1 there across the two windings, and you just turn it to balance out the hum, and it's taken down to ground. I did like the knobs, but unfortunately they sloped off to a very thin point here. If you try to get this knob off, someone else has tried to and snicked the edge of this knob, and there's just a can you see there? It's where someone's put a screwdriver in behind there. If you wanted to get these knobs off and they're rusted on, you've got to be very, very careful. What you'd have to do is you'd have to put a cloth underneath this shiny surface here, and you'd have to put something underneath here, underneath here, top and bottom, up the top there, you know, a screwdriver with a cloth or something there. But don't ever try to get these knobs off just using a bare screwdriver. You'll ruin this highly polished surface here. I found that selector switch to select the different inputs was okay. A bit of what we call lube, electrolube down in here, electrolube in there was a good idea, and just twist the knob around a number of times to get the lube into the contacts. These Yaxley switches do tend to get dirty and scratchy from time to time. I think this one I had to replace the volume control. It was awful. So I had one in the spares box. It's 500k log. I had one that fitted. Yeah. To get everything apart, you have to literally. I wondered how to get it apart, and you have to take. I'll just show you what you have to do. You have to take these screws out here, here and here. You have to remove that there, which is holding the valve base for the EL34 in place. Can you see that screw down in there? That one in there. And you have to take these screws out here, which are self-tappers. Here, get rid of them, and eventually, and you have to take these side screws out here, and this whole thing, this whole frame comes out, in revealing the underside of the printed circuit board. And Pye said, and this is their technical notes, they actually said if you wanted to replace any of these components, rather than take the, that was the other thing, you have to take the you have to unsolder all the windings of the transformer, the output transformer, the mains transformer, and you have to take the mains transformer out and the output transformer out before you can get to the underside. And the Pye engineer said, don't bother to do all that. Snick off the offending component, leaving a tail a little bit behind, and then solder on the tail end the new component. That's what they said. So if you see a repair, you'll see that that's what's been done here, or what I've done there. I've left a tail and I've soldered the new component on top of the tail. There, and so on. So here I managed to heave out the old one and poured solder down the hole and put the new component in, and hope to goodness that it soldered on the underside without actually getting to the underside. I don't recommend people do that, but this one did solder, but I couldn't vouch for the integrity of this solder on the printed circuit board side. The component side, yeah, fine. I could have snicked off the old one and done it, but anyway, in the end, I thought, well, that looks okay. I'll do it with all of them. Then I thought, no, I won't. It's too much bother. So on one of the amplifiers, I did take the whole thing apart. I took the output transformer out and the mains transformer out, took all the screws out, and managed to get it apart to see the other side. And it was in a bit of a filthy state, I have to say, after what, 70 years, was it? No, 1957. Yeah, 60 something odd years, over 60 years. And these are all, I suppose they're like carbon resistors, some of them are high stability, and you'll know whether they're high stability because they've got a pink band on them. I think you can see that one. Yeah, there is, this video is not, there is a pink band on that one, extra one, there's gold and pink. So if you see a pink band on these old resistors, that's high stability resistor. So today, all of these resistors would be high stability, but most of them are 10%, so you've got gold band on them, silver band on them. So they're all, 10 or 20%. Oh, sorry, no, they're not 20. They're 10%. They've got gold, silver. Keep on saying gold. Got a silver band on them, which is 10% tolerance. So there's a wide scope of tolerance, and the designers designed this. They expected quite a wide range of tolerance, except where these high stability resistors were put in. I think there's another one. I think that one is a high stab resistor. That one there, which doesn't look to be, well, it could be the original, who knows. But you can see these are not, I had to put these in. I didn't have anything like it. I didn't like to put ordinary carbon resistors in like that, so I put a 5% in there. Some people would say, right, hang this, let's get this amplifier up to the specification that the manufacturer intended when it was first produced. Let's not compromise. They take everything out and they put high stability resistors, new capacitors, everything. Anything they leave would be the valves, if the valves are okay, the valve bases, the transformers, and that's about it. Everything else would be replaced with modern stuff. But even the pots, if you could get these type of pots these days, potentiometers, all be replaced, and even the input socket, the input sockets here, the DIN phono sockets here, they replaced them with modern equivalent, modern ones. One thing I noticed also about this amplifier was that I think the output socket for the speakers, that's just there, is a 4-pin. I think it's called a tannoy. So you've got the common, then you've got your 4 ohms, your 8 ohms, and your 15 ohms coming out. Well, I expect a lot of people will put a wire in there and a matchstick, but you should really put if you can find one on the internet, it cost about 15 quid just for that socket, which was a common garden tuppenny halfpenny thing years ago, but now you have to pay the earth for them. Oh, I happen to have one in the spares box, and I used that to connect my speaker up on this test to test these. The other thing I noticed, because I couldn't see it on the circuit diagram, but it says in the notes, because I couldn't see a fuse anywhere. I traced up through here. I said, "Where's the fuse?" Okay, and it's there, but I couldn't see any fuse holder, nothing anywhere, and it's inside this voltage selector here, mains voltage selector. If you pull it out and look on the underside, it says fuse there. I've got it upside down. Fuse, can you say it? Sort of Fuse, fuse there underneath. and this sort of polythene cover comes off, and inside there was the most peculiar sized fuse I did ever see. Um, it was small, didn't have anything like that. I had to modify a 15mm fuse. Is it 15mm? Anyway, I can't see to put this back. Anyway, I put it in the wrong socket. That's why. So there we are. It's now put back 230, 250 volts. Just look up here, fuses, somewhere or the other, just to let people know what I did. I found something in here. I just, well, I had to do because it's blue, because I had to use it was smaller than excuse my voice, it was smaller than these ones here. So it wasn't quite that. I did have something, but I don't think very many people would have a fuse that will fit in there. Maybe you can get them on the internet, but oh yes, there we are. I got just about every fuse you can think of, but I ended up having to use one of them that's in there, which is 15mm, 5/8 of an inch, and even that was a little bit long. Oh well, there we are. Such is life. The fuse was inside there, blown, and it was a 1 amp fuse. I think it's a 1 amp fuse, hidden away. Well, there we are. There we are. If anybody's worrying about my voice, don't use a vacuum cleaner with a dust bag that's got horrible dust in it. It's got spores and things, and that's what happened. And then the next day I got a bad voice as the dust blew out the vacuum cleaner and down my throat. Anyway, that's an aside. The other thing is always, as I've said before, always try and use a variac to start these things up. Don't put the full mains voltage on them, or if you haven't got a variac, use on this particular instrument, use a 60-watt lamp, because it doesn't draw that amount of current, and that will at least limit the current to flowing through the smoothing capacitors. And then they sort of heal a bit. I'm not saying they will totally heal. The best thing is to replace these with new ones. And incidentally, you might even not get new ones, but new old stock, which still need to be healed in some way or treated carefully when you get them. Don't assume just because you're buying new old stock it's okay. You've just got to assume that the capacitance is maybe a bit dry, a bit leaky. It's gone a bit high resistance, dried out a little bit, and the foil, the aluminium foil, is not as it should be, and you get this leakage. And if it leaks a little bit and it gets warm, and then it leaks a bit more, it gets hotter and hotter, and it can just die on you quite spectacularly. And that's it. There we are. I think that's about it. I would like to show you. I'd like to scope this, and so I'll close this video down.